So welcome to another semester of learning. This is EE 698G. Lecture 1. So the title of the course is Circuit Design for Phase and Frequency Synthesis. This is a long title. So first let us understand what is meant by this title, right? What does synthesis mean? To create, to generate, etc. Right? What is frequency? 1 by time period. So if you take any periodic signal, it will have an associated fundamental time period, and you can calculate the associated fundamental frequency. What about phase? So for now, simply understand that this is something related to delay. So basically in this course, we are going to learn about circuits that will help you either generate a delay or generate a frequency. And what do we mean by generating a frequency? Basically a clock generation. We are going to create circuits that can create periodic signals. Okay, so this course is all about delay generation and clock generation. So now, when we think of an analog circuit, what is the first circuit that comes to your mind? Amplifier, right? Basically, any circuit that operates on a sensitive signal. So you could have a sensitive signal like this. The amplitude, you would usually see the amplitude being represented in voltage. It could also be a current waveform, but you have a sensitive signal. Now, in this course, we are more interested in the time domain information associated with the signal. Okay. So of course, the time domain information and the amplitude domain information are not independent. They are dependent with each other. But as you will see, there are certain parameters that quantify this time domain information in the signal. And now we will learn about circuits that operate on those parameters. So much like how you have learned to amplify and filter a sensitive amplitude domain signal, we will learn to amplify and filter these time domain parameters. Okay, so we're going to learn about circuits that deal with time as the sensitive parameter instead of just the amplitude. Okay, so that is the key idea between this course, about this course. Now, the most common periodic signal that you would have seen is a clock signal. I am sure you are familiar with clock signals such as a square wave. But of course, this could be any form of periodic signal. I could take a sine wave and this can also act as a clock. Right? For example, if I were working with digital circuits, the most common clock signal that you would have seen would be a square wave or a pulse train. That is a square wave with different duty cycle. Right? But if you're working with an analog circuit, you could be using a square wave clock. You could be working with a sinusoidal clock or even other weird waveform shapes such as a triangular wave or something else. As long as it is periodic, it can technically act as a clock. Okay. So now, can you tell me any application that you have seen with the clock signal? So we said that the most important periodic signal we need to deal with is a clock. What are the applications that you have seen? Right, whole digital domain works on clock. What else? What part of the RF? So up conversion and down conversion. Anything else? Watches, right? Third, yeah, serializer and deserializer, etc. So now a lot of names, applications have been thrown around. So let's take a look at some of them, right? So the first application I would tell would be sequencing and synchronizing events, right? And the best example is we all have agreed to be present in this classroom at 5:15 p.m. And all of us have synchronized with respect to a clock, right? And we have been present here at 5:15 p.m. Now it's a different matter that some of your clocks are slightly out of sync and you came a little late. So those of you who came a little late, please synchronize with respect to the clock here, right? Now let us come to time scales that are much smaller in nanoseconds and picoseconds ranges. And then we come to the example of the processor. So the image you see here is the i7 core processor from Intel. So as you can see, this consists of 6 cores. The level 1 and level 2 cache, which is the fast but small memories, are available within the cores. There is a shared level 3 cache here, and there is a memory controller at the bottom. There are other IO related peripherals on the side. Now, anytime you are running an operation in your laptop, it could be running a MATLAB computation, or maybe you are watching some video. A lot of logic gates need to switch within this processor. Data is getting accessed from the memory, some processing is happening, data is getting pushed back into the memory, etc. Now, all of these events have to be synchronized and sequenced correctly, and you need a clock waveform for that. Now, it's not necessary that the same clock is servicing all the parts of the processor. You might have 1 or 2 clean reference clocks. They will enter the processor, and then they can get divided down, they can get multiplied, and each part of the processor might be running at a different frequency. So let me show you another layout. This is again a different processor from Intel. So what I like about this figure is that it clearly shows how different parts of the layout are being processed by different clocks. For example, are being serviced by different clocks. The regions shown in pink are being serviced by a core clock. Regions in green are being serviced by an IO clock, etc. So these are different clock domains. It doesn't mean that it's again a single clock. You could have a clock and a divided down version of that as a part of the same clock domain. Okay. It just means that the phase relationship between the clocks within that domain is completely known. If you have a clock, getting a divide by 2 clock from it is very easy, and the phase relationship is also completely known. So all of that together will form a clock domain. So you have 3 major clock domains here. Now you can see that there are components called as PLLs, right? Anybody knows the full form of a PLL? Right. So this is a phase locked loop. In very simple terms, you can think about a PLL as a circuit that generates clock frequency. So it's a clock generation circuit. Similarly, you can see that there is something called as a DLL here. What is a DLL? This is a delay locking. So can you quickly count and tell me the number of PLLs in this layout? So you have to sum up the filter PLL, IO PLL, uncore PLL, etc. All of the PLLs have 16. And how many DLLs? Eight, right? So it's just a coincidence that the number of DLLs were half that of the PLLs. It need not be the case all the time, right? So basically a DLL is a circuit that can generate a stable delay. So you have clock generation circuits and delay generation circuits in this layout. And this is a typical case. Any processor you take will easily have more than 15 PLLs in it. The number can go anywhere between 15 to 30, actually. So if you take a mobile processor also, you will find there are a lot of PLLs and DLLs involved in the system. Okay, so now I picked up a table from the Intel website again, and let us focus on the clock frequencies. This is again a desktop processor. So they are listing processors from i9 to i5, different generations of it. And what is the range of clock frequency that you see? So from 2.2 up to 5.8, right? Yeah. So there is a base frequency, the base clock frequency. And under certain conditions, for certain portions of the processor, you can run it at a faster rate. Right? So you have a maximum turbo frequency also given. So the ranges that you see are varying from 2.2 up to 5.8 gigahertz. right? Now, for the next generations, actually the 14th generation is out, but I couldn't find a nice table like this for the same. But you can expect that the frequencies from one generation to the next is only going to increase. No consumer is going to say, I want a slower laptop. Everybody wants a faster laptop, right? So generation of high frequency clocks and distribution of this clock throughout the processor is a very challenging problem. And it gets more and more interesting with new consumer demands. Okay, so this is one major application, which is sequencing and synchronizing the events in a processor, right? So now the second application is the one that you mentioned, which relates to wireless communication. So in particular, this relates to the up and the down conversion occurring in the transmitter or the receiver. Right? So anytime you are using your phone to either access Wi-Fi, Bluetooth, or maybe make a call through LTE, 3G or 4G, you have signals that are being transmitted and signals that are being received, right? And correspondingly, you have a transmitter chain in your chip or a receiver chain. So let me start with a very simplified receiver chain. What is the first component that you need for receiving a signal? Right. So you'll have an antenna. The signals that you receive will be centered around a carrier frequency, right? Everybody understands this? Yeah. So if I were to look at its spectrum, so you'll see that there is some information around some carrier frequency FC. And so I'll plot both the positive and negative frequencies. You'll have the same information on the minus FC side. Now the signal is going to be very weak. So the first step would be to amplify the signal, right? So what do we have to take care while we are amplifying the signal? We don't amplify the noise. But more importantly, because the signal is so weak, so as far as this unit is concerned, it cannot differentiate any noise with the signal. Everything is input signal for it, right? So the thing is, the noise floor of the first amplifier should be much lower than the weak signal you are receiving here. The noise floor of the amplifier will have its own noise. This noise has to be much smaller than the signal that you want to receive. And given that the signal you are receiving is already very low, the noise of the amplifier has to be much lower than that. So you need a low noise amplifier, or in short, we call it as LNA. So this is a low noise amplifier. Okay. So the signal the antenna has picked up is RF, which is centered around FC. What about after the LNA? Because the signal you are receiving here is already very weak, right? If the amplifier's noise is greater than that weak signal, all that you will see at the output is the amplifier's noise. You will not be able to detect the signal. So any noise this amplifier has to be much smaller than the signal itself. So it's a low noise amplifier. Okay? So does the spectrum change after the LNA? It could be amplified, but the information is going to be still centered around FC, right? So you will have the same spectrum here. This is also at RF. So the next part is to bring down this information from carrier frequency to baseband or DC. Now to do this, we multiply this with, right, you have to multiply this with a signal at FC. So let's say we are taking cos of 2 pi FC into T, right? Now, this is a clock waveform. It's a periodic sinusoid. So you will need to generate it using some clock generation circuit. And this we will call as the local oscillator, in short, LO. Okay, and this local oscillator is usually implemented using a PLL. Okay, now this cos 2 pi FCT will look like this if you were looking at the spectrum of that signal, right? So now I am multiplying two signals in the time domain. What happens to them in the frequency domain? They'll get convolved. So how would it look like? So both these components will first come around baseband, right? You will also have some portion of this appearing at 2FC and at minus 2FC. Okay. So now the information you need is around the baseband. You don't want the components at 2FC and minus 2FC. What should you do? You have to low pass filter it. So you add a low pass filter. And this will give you the baseband signal alone. And after this, you plug this, give this as input to an ADC. And you have the digital baseband signal, which you can process further. Okay. So now let us focus on the FC that is being generated by this local oscillator. Let's say you are working with Bluetooth. Can you tell me the value of FC that you will use? Yeah, this will be around 2.4 gigahertz. What if it is Wi-Fi? Yeah. So 2.4 gigahertz, you also have a 5 gigahertz Wi-Fi signal. Okay. Now, if it's an FM radio signal, usually the radio channel's name itself will tell you the carrier frequency associated with it. So one radio channel I could find in Kanpur was Red FM 93.2, 93.5. Right? So what is the carrier frequency then? This is 93.5 megahertz. So now, of course, the specifications associated with the clocks generated for the receiver or the transmitter is going to be very different from the specifications that is required in a processor, right? How clean this clock should be, the type of frequency accuracy and stability needed, etc. are going to be different. Okay. Now, just a quick example. Let's say instead of tuning to 93.5, you tune to, let's say, 92.8 megahertz. So instead of generating a carrier frequency at 93.5 meg, let's say the phone accidentally generated 92.8. What do you think you will hear? So 92.8 is most likely going to be noise. But if you deviate a little bit more, you are listening to a totally different channel, right? So the precision with which the frequencies have to be generated is going to be very tight here. Okay. Is this example clear? Okay. Now, how much in percentages? So this is usually going to be, you will have a narrow bandwidth around the sender frequency, and the channel width is determined by specifications. So FM, I'm not sure what is the channel bandwidth, but there'll be some limited channel bandwidth and you have to be in that range. So any application you take, there will be channels decided and you have to be at the center of the channel to get maximum signal. So these are the two major applications. We have now covered synchronization as well as the wireless communication part. Now you can also have wireline communications. So for example, if you take a chipset on a PCB or chiplet communication, you will have multiple blocks that need to communicate with each other. Multiple chips on the same PCB, for example. Maybe you have a memory, external memory, and it needs to communicate with the processor. So these are wired communications. And to do this communication, you generally have a protocol called as serializer, deserializer inbuilt. And the clock generation for this is also a little tricky. Clocks and periodic signals are required in radars, in circuit called as time to digital converters and digital to time converters. So the time to digital and the digital to time converters can be thought of as the equivalent of analog to digital converter and digital to analog converter. In analog to digital converter, you are converting the amplitude information to time. In time to digital converter, you are converting some sort of time information into digital. It could be the delay between two rising edges or the delay of a rising edge versus a falling edge, etc. Similarly, you have digital to time converter where you give a digital code and you get a delay as the output. So these are some of the applications, of which the first three applications are something that you deal with on daily basis. Now, in this course, we will initially start by looking at delay lines. Then we'll take this delay line and put it in a negative feedback. So that gives you the delay lock loop. Then we will learn how to analyze these signals. In particular, we will learn how to do small signal analysis. Now, all of you have seen small signal analysis, but you have done that in terms of either voltage or current, right? Now we are going to learn how to do this in phase. Time is the small signal that you are dealing with. Then we will also do noise analysis. Finally, we'll learn how to build an oscillator. We'll keep this oscillator in negative feedback, and that gives you a phase lock loop. So by the end of this course, you will learn how to use feedback in time domain circuits. You will learn how to analyze these circuits, and you will also be able to design DLLs and PLLs. So we have two teaching assistants, Ruji and Piyush. And this is the grading scheme. All the components have 25%. So the first component could be, if any assignments are given, that will also contribute to the 25% allotted for mini quizzes. Now, mini quizzes, if we take n mini quizzes, the best n-1 will be chosen for each student. There are no surprise quizzes. Not n-2, n-1, right? But there are no surprise quizzes. Again, there is no particular course reference. You are expected to follow the lectures and do the assignments and tutorials carefully. But the course content has been built based on these resources. So we have the design of CMOS phase lock loop from circuit level to architectural level by Rasavi. There are also very good video lectures on phase lock loop by Dr. Saurabh Saxena from IIT Madras. If you search for these topics, you'll find the video lectures. And finally, our holy grail, design of analog CMOS integrated circuits by Rasavi. So now the MOOCit for this course is already up. If anyone is yet to be added to MOOCit, please drop me a mail. All the course announcements and resources will be uploaded here. Now, I'd like to take some special classes in the beginning only, so that even if we lose some class in between, we don't have to worry about taking a special class towards the end of the course. So first special class will be on coming Saturday, 13th Jan. Right? I'm planning for 11:15 to 12:30 p.m. Anyone has a clash with that slot? I think that ends before 11, right? So 11:15 a.m. to 12:30. Coming Saturday, right? And the Saturday after that from 11 to 12:30. So this will be a class plus your first mini quiz on 20th Jan. So the first coming Saturday and the Saturday after that.
We have a class on 20th.
What time is it? 11 to 12, is it? 613 has a class from 11 to 12:30. Okay. 11 to 12. But I think class immediately after might be very tiring, right? So we can do it from say 3 to 4:30. No, 13th I have some other stuff going on after that. So 13th it's morning, 11:15 to 12:30. On 20th January, it's from 3 to 4:30 p.m. So we'll have a mini quiz and a class on 20th. Okay. Sorry? No, on 13th, it's from 11:15 to 12:30. On 20th, it's in the afternoon. I'll send out a mail with the timings. Any questions in general about the course? It is not compulsory to attend 613, but if you're looking to specialize in circuit design, then the recommended flow is either E210 or E610. then 613, then any of the advanced courses, right? But you can do 698G without 613. But again, if you're looking to specialize in circuit design, take 613 at some point. Whether it's after or before, it is okay. So this course will require some basics of analog, digital, control theory basics in terms of feedback, stability of a feedback system, negative feedback, positive feedback, etc. And a little bit of signal processing. Like if given a signal, you should know what are the frequency component in it and how to calculate those frequency components. A little bit of Fourier analysis, basically. So this is a requirement. Now, if you have not seen 613, you might have a problem with the noise analysis part, but I can give you additional material so that you can catch up, right? We don't go into detail with respect to noise. We'll do things at a top level. So you should still be able to manage it. Any other questions? If not, we can start with some basics in this course. So first, let us look at the relationship between phase and frequency. So let us consider a signal y of t equal to a naught into cos of omega naught t plus phi naught. Okay. Here, a naught is the amplitude. If this was a voltage signal, a naught will have units of volt. The argument of the cos is what we'll call as the total phase, or sometimes just phase. And this will be represented using the variable phi. Total phase is a function of time. So usually we'll show this as phi of t. Okay. What is the unit of phase? Yeah. This is in radians. Now let us look at this omega naught. What is omega naught? Omega naught is angular frequency. What is the unit? So this is represented in radians per second. How is it related to frequency in hertz? So this is equal to 2 pi times f naught, where f naught is represented in hertz. So omega naught is angular frequency. F naught is what we call as frequency. But from here on, we'll use the term frequency interchangeably for both omega naught and f naught. Right? This is with the understanding that whenever we write omega naught, it is represented in radians per second. And if we write f naught, it is in hertz. But the same term frequency will be used interchangeably. And how is this related to the time period of the signal? So this is 2 pi by the period t naught, where t naught is represented in seconds. Okay. Now this phi naught is what we call as the initial phase, or sometimes it's also called as the phase offset. Now, some of you may have seen the notation where when you say phase, they refer to this phi naught, right? So we are using a slightly different notation. For us, phase is the total argument shown here, and initial phase or phase offset is going to represent our phi naught. So anytime you come across these terms in a new article or a paper, please go and check what is the definition they are using. Okay. So any questions on this? This is something that I believe all of you know. So let me give you a small problem to try out. So the first exercise is, let's say you have y of t equal to a naught cos of omega naught t. So you have to plot y of t, the total phase phi of t, and the derivative of the total phase with respect to time. So please try. So let me mark the time period as T naught. To T naught, etc. Okay. So to sketch find phi of t versus time, what is the expression for phi of t? So this is omega naught into t, which is 2 pi by t naught into t. So at t naught, what is the value of phi of t? That should be equal to 2 pi. At 2t naught, this should be equal to 4 pi. So this is a very interesting result. With every t naught, with every time period, you are accumulating a phase of 2 pi. Right? So this is a result that you can remember. With every time period, you have a phase accumulation of 2 pi. Now, what is d phi by dt? So d phi by dt is called as the instantaneous frequency. Okay. In this case, this is equal to omega naught. And that is same as the slope of this curve. Right? So now to plot d phi by dt. This will be a constant omega naught. Okay.
And for phase after shouldn't we start from 0 again?
So the question is whether you want to plot the total phase like this or you want to plot the phase like this. Right? So both of them are equally valid representation. So because we have defined phi of t as 2 pi by t naught into t, based on this expression, you can draw the straight line. Okay? So as you will see later, there are certain aspects of analyzing the phase signal that becomes easier when you have the linear plot like this. Right? If you wrap the phase around and bring it to 0 and then plot, that is also a valid expression. Nothing is wrong there. But certain analysis can get a little tricky. In fact, the idea that the phase signal will wrap around by its own is used in certain circuits, such as ADCs. Okay, so both of them are correct. We'll stick with this definition and use the one that is linearly increasing. Okay, now let's say I consider two time points here, T1 and T2, and I integrate this waveform. So basically, I'm looking at the area under this waveform. What does this information give you? Is there anything significant about this? It gives you the phase change, right? So let me quickly write that down. So what I've done is integral of d phi by dt from T1 to T2. This is basically phi at T2 minus phi at T1. So I'm looking at the phase at T1 and the phase at T2, and I'm finding the difference between them. So integral of the instantaneous frequency gives you the phase change happening in the total phase. Okay. So now here is a problem for you to work out. This is a homework problem. Let's say I give you the y of t with some initial phase. So you still have to plot y of t, the total phase phi of t, and the instantaneous frequency, which is derivative of the total phase. So let me give you another problem to work on right now. Let's assume that I have a y of t given by sine of some total phase. I'll give you a diagram for this total phase, and then you have to sketch y of t for me. Now you have to plot y of t. T1 is some time instant given to you. It's up to you to make sense of that. This is 4 pi. This is 2 pi. So now here we see that in one T1, you have a 2 pi accumulation, right? That means one time period is over in one T1. So you'll have the first cycle like this. From T1 to 2T1, you again have a 2 pi accumulation. Now, for the next 2 pi to accumulate, you are taking time from 2T1 to 4T1. Therefore, your signal has to look like this. Okay, and you can calculate the frequency of the signal from 0 to 2T1 and 2T1 to 4T1 by looking at the slope of these waveforms. Let me call this as omega 1 and omega 2. What is omega 1 now? This is 2 pi by T1. And what is omega 2? It is 2 pi by 2 T1 or equal to pi by T1. So what is the relationship between omega 2 and omega 1? It's half of omega. Okay. So now given a phase waveform and given how it is represented, you should be able to show me what is y of t. Okay. So one last exercise. Let's say you have a signal given by y of t is equal to cos of omega naught t plus some initial offset phi naught, but this phi naught is now a time dependent function. Okay. So let's say omega naught is given by 10 power 8 radians per second and phi naught of t is given by 0.01 cos of 10 power 6 t. Okay, your initial phase offset or the phase offset is now not a constant, it is a time dependent function. So you have to calculate the instantaneous frequency. Now, the instantaneous frequency is not a constant, so I have to give you a particular time point at which you have to calculate. So calculate this for t equal to pi by 2. You are calculating the instantaneous frequency of y. So now after you have done this part, and something interesting for you to try out is to plot y of t and d phi by dt. So as well as phi of t. So now to plot this, you can take the help of any simulation tool such as MATLAB, right? So plug in all these values and observe how these waveforms are changing. Okay, so this should now give you some idea about the relationship between phase and frequency. Now let us look at how phase and delay are related. Did I start recording? So let's assume that I have an ideal buffer with a delay of delta. Okay. So if I give an in of t here, the out of t will be a delayed signal, right? In other words, if this is my in of t, the out will be delayed by some delta. Okay, so we are looking at ideal delay element. Can you tell me the relationship between out of t and in of t? How can I write this in terms of in?
Out of t is a phase or a signal?
Out of t is a signal. You can think of it as a voltage domain signal.
T plus T minus delta.
So this will be t minus delta. Okay. Now let's say my in of t is a sinusoid. Okay. Let's say this was sine of omega naught t. Can you derive an expression for out of t? So this will be equal to sine of omega naught into t minus delta, which is sine of omega naught t minus omega naught into delta. I can compare this to the original formulation with the standard form we had, which was sine of omega naught t plus a phase offset, right? So now what is the expression for the phase offset? This is minus omega naught into delta, or it is also equal to minus 2 pi by t naught into delta. So if you have a delay, to convert that into phase information, you simply have to multiply it with the frequency omega naught, right? And then add a negative sign. Does the negative sign make sense? Because when you have introduced a delay, you have reduced the total phase of the signal, right? So hence the negative sign. Okay. So you either multiply it with omega naught or you multiply it with 2 pi by t naught and add a negative sign. That is the phase that you have introduced, right? So the relationship between phase and delay is very straightforward, which is why we tend to use phase and delay also interchangeably sometimes. So delay is represented in seconds, phase is represented in radians, but this is a relationship that relates both of them. Okay. So if you have a single sinusoid, now you know what to do. What if you have a signal, a periodic signal, which consists of multiple sinusoids, right? For example, let's say I have a square wave. And now I am passing the square wave again through a buffer, right? And this has a delay delta. Now, a square wave like this can be represented as a summation of multiple sinusoids. So if the fundamental frequency was omega naught, I'll have n omega naught into t. The strength of each of these components is given by 4 by n pi. And you sum it up for odd ends, right? So now you have multiple frequencies in the system. You know that you have delayed the signal by some delta. How do I convert this delta into phase information? Why minus omega naught? I have a lot of frequencies. So the general practice is to still rely on the fundamental frequency, right? So I can represent this as some function gamma of omega naught t, where whenever I see gamma of omega naught t, I have to replace it with this above expression, right? And then if you analyze, you will see that out of t is again equal to gamma of omega naught t minus omega naught of delta, right? And then we say that the phase associated with this is again equal to minus omega naught delta. So if you're dealing with a periodic signal, which is a composite signal consisting of multiple sinusoids, and you want to express the delay in terms of phase, you still rely on the fundamental frequency. Is that clear? If you want to convert the delay information into phase, you multiply it with the fundamental frequency of the system.
You want to write phi of t, then what will you write?
If I have to write
Phi of t of the in signal.
in signal,
Yeah.
So now the initial phase, let's assume that the int also had some initial phase. Let's call it as phi n, right? Now you will have phi n minus omega naught of delta for the out. So given how I have plotted here with t equal to 0, the initial phase would be 0 for int t. If this is the plot of int, right, then the initial phase is 0. You will have to, so the you can represent it as gamma of omega naught t, and then you can say that the total phase is some omega naught t plus phi naught, which is 0 here. Okay, so if you're talking about a square wave as a clock and you are interested in its total phase and its initial phase, etc., you tend to look at its fundamental frequency. Now, there are certain applications where you will be interested in individual frequencies. Then you may have to talk about the total phase of the individual frequency component. But when you deal with square wave as a clock that is getting generated and distributed, you look at the fundamental component. Okay.
So if a signal like sine of omega t plus sine of c omega t is given, those two terms,
then you look at the fundamental. Yeah. Depends on the application, but if you are interested in the generation distribution of clock waveforms, you look at the fundamental. So any questions on this relationship?
Phase delay is the phase delay of the fundamental frequency of light.
Correct. Yeah. So now we look at delay lines. Right. So what is a delay line? What do you think it should be? Yeah, some element that is giving you a delay, right? So now delay lines can be broadly classified into two categories. So the first category is what we call as a true time delay line. So let's assume that you have a signal like this, right? This is your input. And you want to delay this signal by some amount while preserving the wave shape as it is. This is called as a true time delay line. Now, the other category is where you delay only the edges, especially that of a clock signal. Right? So if you have a square wave, let's say something like this, and then you are interested specifically in delaying these edges. So your output will look like this, where you have delayed these edges in an accurate manner. Now, it's possible that the original signal had some minor variations when it was high, right? It is okay even if you don't replicate that exactly. Or maybe in adding a delay line, you might have introduced some minor noise here. This is also fine as long as the edges have been delayed correctly. Okay, so this is a simpler form of a delay line. So in the first case, you want to preserve the waveform shape as it is. The amplitude information also needs to be preserved. In the second case, the information you need is only in the edges of the signal. Okay, so this is the difference between the two delay lines. Now, a true time delay line can be implemented using a transmission line. It can be implemented using LC delay lines. Or you can also use active implementations, which means there'll be transistors involved. And all of these are basically all-pass filters. So you create an all-pass filter to obtain a true time delay line. Now, in this course, we will not be focusing on the true time delay line. I'll give you a minor exercise problem to get used to some nuance involved. But other than that, our focus is only on delay lines, which delay the edges. Okay. But if you are interested to learn more about this, then Dr. Raymond Montel works extensively on this topic. You can refer to his PhD thesis. This has been uploaded on his website. Okay. Now, how do you think we should construct the second type of delay line? What do you think should be the building block? Digital? So what should it be? CMOS inverter, right? So you put a CMOS inverter, put two of them together, it becomes a buffer. Put a chain of buffers, it gives you a delay line, right? But I'm going to put it in quotes because the circuit implementations you're going to see now are inspired from CMOS inverter, but we are going to tweak them to meet certain specifications, right? So before we get to that, now we have to quickly do a recap of CMOS inverter to make sure that all of us are on the same page. So how does a CMOS inverter look like? This has a PMOS and an NMOS transistor. This is the input node. This is the output node. This is a symbol that all of you are familiar with. If this is a supply rate VDD and this is 0. By the way, you can give negative supplies also. It need not be 0 and VDD. If you give 0 and VDD like this, and you have a signal going from 0 to VDD, the output is going to switch from VDD to 0 and vice versa, right? How do we define delays in a CMOS inverter? So let's start with TR and TF. So if you have a signal, a rising edge that is going from 0 to VDD, what is the most common definition used for TR? You look at the point where it has reached 10% of the output to 90% of the output. And the delay between the two gives you the TR. Now, the definitions can vary slightly depending on the application and the context. For example, if you're working with a simulation tool and you're using a voltage source to generate a square wave, there when you put in the TR and TF values, it usually refers to 0% to 100% points, right? But when you deal with real signals, you'll see that there is some noise involved in the logic high and logic low levels. So to not get confused with the spikes of the noise around the rising portions, we look at 10 to 90% in the output waveforms. Now, if the low and high values had a lot of noise, maybe instead of 10 to 90%, it makes more sense to look at 20 to 80%. So if you're deviating from the 10 to 90% threshold points, please mention it explicitly, right? Similarly, for TF, for a falling edge, the threshold points are 90% to 10%. And you measure the delay between them. This gives you the fall time. Okay, is this clear? What is the definition for TP-LH and TP-HL? Right. So let's start with TP-LH. Tell me what is the input waveform, what is the output waveform? Which is high to low? Input is high, right? So for TP-LH, your input is going from high to low. The output is going from low to high. So the LH here refers to the output. The threshold points we consider are 50% and 50%. So this is 50% of the final output line. And this is your TP-LH. Now, there are, of course, other definitions for TP-LH. For example, some definitions will include, will use the threshold values as maybe VIH or VIM. That is one possible definition. In certain other cases, maybe it makes sense to use a different threshold value. For example, the 50% threshold makes sense if the trip point of the inverters are close to VDD by 2. If they are very different from VDD by 2, maybe it makes sense to use the new trip points as your threshold voltages. It can vary from application to application. In this course, we will stick with this 50% threshold values. Similarly, the TPHL so this is high to low, which means your output is going from high to low. So your input should have gone from low to high. You look at the 50% point for these two signals. And the delay between them gives you the TPH. Is this clear? So our next step is to calculate one of these. Let's say we calculate TPHL just so that you get used to the idea of calculation. I'm sure half the class has already seen it in 619, but let's still go through the steps, right? Now, before I get to that, quickly tell me if I can apply small signal analysis. So this is an analog course, basically. So does it mean that if an inverter is being driven by a clock, switching from 0 to VDD, I can apply small signal analysis? Why not?
Changes that we are having here is large.
How do you define large?
Compared to the bias point of transistor.
Regions of operation of the transistors are changing. So you were saying something?
The output voltage is coming from VDD to 0.
Huh.
So changes very much compared to the bias. They are to the transistor.
Right. So now we have learned that small signal analysis can be applied when the signal applied, the small signal applied is much small compared to what?
0 to VDD.
Not 0 to VDD. Compared to the bias point, right? So your Vin has to be much smaller compared to twice of VGS minus VTH. This is not true if you're giving inputs to the inverter varying from 0 to VDD, right? Even if you imagine your bias point as VDD by 2, and then there is a signal switching from, there is a VDD by 2 amplitude signal riding around the VDD by 2 bias. So they are comparable. So this assumption is not valid, right? So you cannot do small signal analysis. Even the region of the operation of the inverter of the transistors are changing, okay? So with this in mind, let us now try and calculate the TP high to low for an inverter. What should be the input signal that I consider?
Yes.
Why step? Why is the analysis very difficult? So you're telling me that I should consider an input like this and the output is like this, right? So why is the analysis very difficult? Yeah. So now you will have to look at the, if I gave a signal like this, right, I can still solve it. I will have to look at the time instant at which the transistor is turning on, NMOS is turning on, and with what value of current it is turning on, and how the current strength is slowly increasing. I'll have to look at the time instant at which PMOS is turning off, and again the strength of the PMOS current as it is turning. So the calculation is getting very complicated. What is the other assumption that we usually make? Did you make any other assumption in 370 or 619 when you did the calculation? Tell me about the capacitance, right? So let's say we have some total capacitance C total here. Let's say this was driving another inverter. What contributes to this total capacitance? Right. So self-capacitance of the inverter. This corresponds to the CDB capacitance, the drain to bulk capacitance of PMOS and NMOS, the gate to drain capacitance, etc. So all the capacitance associated with the inverter itself, and connected to the output and ground, we are calling it as a self-capacitance. What else? Right. Input cap of the next stage. And finally, the parasitic capacitance associated with the routing. So what assumption do we make with respect to these capacitances to simplify the calculation? They remain constant, right? So the C self is actually a function of the bias voltage that it will see. So as your V0 is changing, the value of the C self, because it is a function of the drain to bulk junction voltage, right? The C self consists of the drain to bulk capacitances and the gate to drain capacitances. These are a function of the junction voltages, which is going to vary as you change the V0, right? Which means as your capacitance is discharging, the capacitance value itself is changing. It's a very nonlinear capacitance. But to simplify the calculation, we are going to assume that the C self is also constant. The total capacitance remains constant as the V0 value is discharging. Okay. So if this portion is not clear, feel free to talk to me after the class, or you can go back and refer to 619 and 317. Now, why are we trying to simplify the equation? Why not solve the complicated equation? Right. So we have powerful simulators. If you want to get the exact value, use the simulator to find the exact value. Our aim in doing these calculations is to get a feel for how the values are going to change when you change the W and L, right? To develop designer intuitions. So now with this step input assumption and the total capacitance being constant, let us try and analyze how to solve this. So at t equal to 0 plus, what is the value of Vn? Vn is equal to VDD. V0? At t equal to 0 plus. Why 0?
Okay, sorry. VDD.
Right? So you are still at this point. It is just about to start discharging. So V0 is also equal to VDD. What is the region of operation for PMOS? Why cutoff? So the source to gate voltage is VDD minus VDD, which is equal to 0. So PMOS is in cutoff. What about the NMOS transistor? How do you find it?
We find it.
You have to find the minimum of 3 voltage values, right? So minimum of VGS minus VTN, VD sat n, and VDS. What is VGS minus VTN here? VDD minus VTN. Of course, VD sat n is some constant. What about VDS? This is VDD. So what region is it likely to be in? So, right. So it cannot be in linear region. It is either going to be in pinch off saturation or it will be in velocity saturation, right? So if I assume short channel transistor, it is in velocity saturation because VD sat n is going to be the smaller value. If I assume a long channel transistor, it will be in pinch off saturation. So in digital circuits, we assume that the transistors are short channel and went mostly with the VD sat n being smaller value, right? Now in analog circuits, you are likely to find both long channel and short channel transistors, right? Since we have already done calculations with short channel transistors, we'll now assume that this is a long channel transistor and then do the calculation, okay? So we are saying that we are going to assume long channel transistors. So the NMOS is going to be in pinch off saturation, right? So now whether we are actually dealing with short channel or long channel transistor, the method for derivation is going to remain the same. So focus on the method for now, because in future, even if you're dealing with a very different device with a very different IV characteristics, you can simply apply the same idea, the same methodology for deriving the delay, right? Okay, if I assume long channel transistor, what is the current equation? Okay, mu and COX, W by L, VGS minus VTH, whole square by 2. What are we missing? Into 1 plus lambda VDS. So the ID VDS curve we are looking at is this. Okay. Now, to calculate the delay, let's start from the basics. What is the current through the capacitor? So you can model this as a PMOS, which is acting as a switch that is open. Your NMOS is now a current source, IDS, which is a function of V0, and it is discharging some total capacitance, right? And this is V0. Okay. What is the other model that you have seen in digital circuits? Yeah. You replace this with an effective resistance, and then you are discharging the capacitance through this RC network. What was the reason behind choosing this as the model to calculate delay in digital circuits? So this is an RC circuit. Even if you have a complicated pull-up and pull-down network followed by a long routing, you can model all of them as different RC, right? You are still ending up with an RC network. And once you have an RC network, you can do Elmore's delay calculation to find out the delay, right? Now in this course, especially, in future, we will have to do analysis of noise. And for that, this particular model is much easier. So right now, we will stick with the capacitor being discharged by a current source model to calculate the delay. So let us start with I'll set up the equation and then I'll ask you to solve it as homework. So the current through the capacitor is given by C dVc by dt. Now, let's say I'm applying this particular scenario. How would the equation look like? Right. You need a minus sign. Why a minus sign? Right. The current is getting pulled out from the capacitor. Right. So now I can write dt as equal to minus of C total divided by IDS into dV0. I integrate dt from 0 to TPHL. Right? So your input is now a step input. The output is falling like this. Now you've identified the point at which it reaches VDD by 2. The delay between these two is your TPHL. So if I assume that this is t equal to 0 point, this is t equal to TPHL. Correspondingly here, what are the integration limits? This is going from VDD to VDD by 2. Okay. So now in this plot, let's for now assume that this is your VDD minus VTN. You have VDD here and VDD by 2 here. If this assumption holds true, then you are moving on this region of the curve. Okay, which means your transistor is still remaining in pinch off saturation. So why don't you substitute these values and calculate what TPHL is, and we can start from there in the next class. Thank you.